All right, today we're going to dive into one of the biggest aha moments in the history of science. And we're going straight to the source, James Clerk Maxwell's incredible 1873 book, A Treatise on Electricity and Magnetism. So, to really get what a huge deal this was, you got to ask yourself this question. Because back in the early 1800s, if you asked the smartest people on the planet this, they'd probably just shrug and say, nothing? I mean, they were seen as totally different things. Think about it. You had electricity, right? This kind of weird invisible fluid that made sparks and zapped you. Then there was magnetism, that spooky force that made compasses do their thing. And then there was just light. They were like three totally separate puzzles, and everyone was working on them in their own little corners. Okay, so let's pick up the first piece of the puzzle. It's something we've all messed around with, right? Magnets. So what did they really know about them back then? So check this out. This is Maxwell's own definition, straight from his book. It's so simple, isn't it? He's not getting all technical about fields or atoms or anything. He's just saying what you or I could see. Hey, it's a thing that points north, and if you poke it, it wobbles back. That's it. And the rules for how they behaved? Just as simple. You know this stuff from science class. Maxwell points to guys like Coulomb, who figured out that opposites attract and likes repel. And honestly, for a long, long time, that was basically the whole story. Magnetism was its own thing, all neat and tidy in its own little box. But that neat, tidy world, it was about to get blown wide open. Those walls they'd built between these different forces were about to come crashing down. And this was the first crack in the wall, the big one. Scientists figured out that if you send an electric current through a wire, it creates a magnetic force. Whoa, that's no coincidence, right? That's a massive clue that these two things everyone thought were separate were actually connected. So how do you even prove something like that? Well, a guy named André-Marie Ampère, who Maxwell talks all about, was an absolute genius. He came up with these incredible null experiments. So instead of trying to measure some tiny force, he'd set things up so the forces would perfectly cancel each other out to prove his point. Like he showed that a wiggly wire had the exact same magnetic pole as a straight one. It was brilliant. And it proved, without a doubt, that electricity and magnetism were two sides of the same coin. Okay, fine, they're linked, we got it. But how? How does a current in a wire here make a compass needle move way over there? I mean, there's just empty space between them. This was the next big, baffling question. So there were basically two camps, two big ideas about how this worked. And right here, Maxwell himself tells us which team he was on. He completely threw out the idea of spooky action at a distance, and instead he went all in on an idea from another legend, Michael Faraday. Faraday's idea that space isn't empty at all. And this is the huge difference, right? Action at a distance is kind of like magic. A magnet over here just instantly affects a magnet over there. Poof, no travel time, no nothing. But the medium idea, what we call a field today, is totally different. It's like dropping a rock in a pond. The magnet creates a ripple, a disturbance in the space around it, and that ripple travels out and eventually pushes the other magnet. It takes time, it's physical. Now, Faraday was this amazing, hands-on guy, but he wasn't a math whiz. He pictured these fields as lines of force, just like when you sprinkle iron filings around a magnet. It's a beautiful, intuitive image. And what Maxwell did, his true genius, was to take that picture and translate it into math. Pure, powerful, undeniable mathematics. And that brings us to the main event, Maxwell's grand synthesis. This is seriously one of the most beautiful and powerful theories in all of science. He took all these scattered bits and pieces, all the experiments, all the weird ideas, and he wove them together into one perfect whole. This is the core of it. He managed to boil down everything known about electricity and magnetism into just 4 now famous equations. And these weren't just a list of rules. No. This was a completely new instruction manual for the universe. It was like he'd figured out how the fabric of reality itself worked. And hidden inside these elegant equations was something mind-blowing. It wasn't just that electricity could make magnetism, it was a loop, a constant dance. A changing magnetic field creates an electric field, which then creates a new magnetic field, which creates a new electric field, on and on and on, forever. It feeds itself. This perpetual dance between the two fields, it led Maxwell to make a prediction.
A prediction so wild, so completely out there that it would literally change everything. This is the big finale, folks.
He realized, wait a minute, this dance doesn't need a wire. It doesn't need a magnet to keep it going. Once you kick it off, this ripple of electric and magnetic fields can just travel through empty space, all by itself, as a wave, an electromagnetic wave. So naturally, the next question is, how fast? How fast would this wave travel? And here's the crazy part. The answer wasn't just some random guess. The speed was baked right into his equations. It was determined by two numbers, two constants that people had already measured in labs, numbers that had to do with how strong electricity and magnetism are.
So Maxwell grabs the latest, best measurements for those constants from 1868, plugs them into his equations, and he calculates the speed of his imaginary wave. And this is the number he gets, a ridiculously, unbelievably fast number.
Okay, so just hang on to that number, because at the exact same time, other scientists were trying to measure the speed of light. And the best measurement they had at the time was this one. Just look at those two numbers. They're basically the same. The speed of his made-up wave was the speed of light.
The conclusion was just staring him in the face. And Maxwell, with this amazing coolness, just states it. It's not a coincidence. Light is one of these waves. Lightning, magnets, sunlight, they were all just different faces of the exact same thing, electromagnetism.
I mean, this wasn't just, oh, cool, we solved a puzzle. This fundamentally changed how we see reality. And it paved the way for, well, for basically the entire world we live in today.
Seriously, his legacy is just insane. His equations didn't just explain the light we can see. They predicted a whole bunch of light we can't see, like radio waves, which wouldn't even be discovered for years. This stuff was so fundamental, it became a cornerstone for Einstein's relativity. And today, everything, your phone, your Wi-Fi, the radio, GPS, all of it runs on this one beautiful idea. You're using Maxwell's equations every single day.
So yeah, a story that started with a little compass needle ended up completely rewriting our understanding of the universe. It showed us that everything is way more connected than we could have ever dreamed, which, of course, leaves you wondering, right? What's the next great unification? What other massive secrets are just sitting there, waiting for the next Maxwell to connect the dots?